Start. Awesome. Welcome, everyone. This is Deep Learning Adventures, a fun and engaging meetup where we talk about data science, machine learning, and deep learning. My name is George. I'm joined by friends all around the world and all around the country. So thanks, everyone, for joining us tonight. I want to welcome my great co-organizers and friends, David and Robert, as well as our two great friends and speakers today, Dimitri and Alexandra, who will be talking about game AI, reinforcement learning, and some new cool concepts that we haven't come across yet. So this is the last course in our Kaggle Mini Courses adventure. We still have a couple more sessions coming up related to that, but in terms of curriculum, this is the last course in the series. And let me share my screen now so I can give you a little more information if you're joining us for the first time. So you can find us on Meetup under Deep Learning Adventures. This is today's session. We record all our sessions and we post them on our YouTube channel, and I'll post a link pretty soon here in the chat. As you've seen, we've covered data visualization, machine learning, SQL, some geospatial analysis, micro challenges. Then we covered an introduction to NLP and computer vision, which was very interesting. The last one we did was 2 Kaggle competitions. Neil and I covered this flower detection or classification competition from Kaggle, as well as this cassava leaf classification. Today we'll talk about game AI and reinforcement learning, which is a cool concept, cool new module. As you've seen, I haven't had the time to do the exercise yet, so looking forward to that. And maybe talk a little bit about this ongoing simulation competition as well. That'd be awesome. I tried spending some time looking at the code. I find it interesting that the environment that Kaggle is using, I just started looking at it. I haven't gotten too deep far, but it was interesting to me how the games were being simulated and so forth. Cool, I'll stop sharing and hand it over to Dimitri and then Alexandra for our first few sessions. Let me stop sharing. And Dimitri, the floor is yours.
Okay, let me share the screen. Can you see my screen?
Yes.
Yep. So this section consists of four exercises. So I'll be covering the first 3 when we'll be discussing the ConnectX game, and then build a few agents that play that game. Then Alexandra will cover the deep reinforcement learning. So let me start with the first section. Okay, there we are. So they describe the ConnectX game, which many of us may be familiar with, especially those with kids. So if you can see the screen, so it has this video simulation of how it's played. It's basically this vertical board with slots, and two players play consecutively, dropping these yellow and red discs, and the objective is to build 4 in a row. In this particular instance, this is the classic Connect 4, which is 6 by 7. And so your objective is to build 4 in a row, either horizontally or vertically or diagonally. So that's the whole point of the game. It's a very popular game. Actually, so it's been studied extensively, and so it's known that the first player can always win by dropping the disc in the center. But if, for example, the first player drops the disc, in the first or second column, it's guaranteed to lose. So it's a well-studied deterministic game, right? So there is no element of chance. It's unlike backgammon or poker or anything. It's fully visible, so we have all the information, and so therefore, quite often, people start studying game theory with this ConnectX game. So Kaggle created a a world of players of Connect4, ConnectX. So the agents that we'll be creating, they compete in the in this universe, basically playing multiple games against each other. And so there is no in contrast with supervised learning challenges. There is no immediate metric of goodness or badness of the model. So the agents continue playing against each other, and then there is some cumulative score that is being developed. So my agents that I created a few days ago are still part of the competition, and we'll look at them. Yeah, they describe how to join the competition, and then they created this Kaggle environment for this particular game. So this is the game. They have this widget. So basically, this is how it plays. In this particular case, they created a spatial agent called random, which is basically choosing one of the 7 columns at random and seeing what happens. We can go back in time. So this is a cool visualization of how the thing happens. And then, okay, so let's just, in the interest of time, I'll go through this section quickly. So how to define the agent. The agent takes 2 arguments. It's OBS, which observations, and config. Observations is basically, let me go straight here. So observations contains this board element, and the board is basically a Python list describing the current configuration of the board. So the zeros, so this is just a reshaped 6x7, so 42 elements. The zeros are empty, and then the 2 players are 1 and 2. So this one list of 42 elements fully describes a current configuration of the game. So maybe it's worth spending just a little time discussing why it's not a supervised learning problem. And so there are a few reasons for that. One of the reasons is that there are too many possible configurations. So there are about 4 trillion possible configurations of the game, and also there is no immediate sort of diagnostics of whether the configuration is good or bad. I mean, Connect4 is a very simple case, but if you think about like a game of Go, which was recently cracked, right, a few years ago by AlphaGo. In Go, they say that it's practically impossible to come up with a good heuristic sort of value function to determine whether your current configuration is good or bad. So it's not possible to come up with the labels. Basically, we lack labels in this case, and so that's why we have to rely on some other sort of algorithms and approaches of how to optimize the play. And so that's why the game AI and reinforcement learning are actually used for these types of problems. So this is how we define the agent. So observations and config. Config is basically the configuration of the board, 6, 7, and 4 in this case. And the first thing we do is we understand, when can we actually drop the disk. And so if you try to drop the disk in a column that is already full, you lose the game. So basically this valid moves gives you those columns that are still available, where the observations equal 0. And so the random agent basically determines which columns are available and picks a random move, picks a random column among those columns. So another agent, the second one that describe, always picks the middle column. So no matter what, they always play in the same place, and the third agent plays, the leftmost column, basically the leftmost available valid column. So these are just starters to understand how the agents actually play against each other. And so here we are in this env environment.run. We can actually run the agents once, one against the other. And so in this particular case, we match the leftmost agent with the random agent. And let's see what happens. So this blue one always plays in the leftmost available column. And as you see, it quite often actually wins, because it sort of piles up the tokens, the disks, in one column, which has a bigger probability of winning than just randomly dropping it all across the board. And so one thing they also do, they provide this get win percentage function, so that you can evaluate the agents against each other. And in this particular case, the middle agent wins 69% of the time, and the random agent wins 2% of the time. The leftmost agent is even better, 84% of the time. But these agents are, as I said, just placeholders basically, and we'll look at a more sophisticated agents when we do our exercise. So let me switch to the exercise.
Can I ask a couple of questions, Dimitri?
Sure. Yep.
So this 6x7, is that like a classical version of
this?
Yes.
Yeah, that's the classical version.
Are there other versions of this game?
You can, I haven't seen them, physically as a game. I always is, 6x7, but in this environment, you can simulate basically any board. With this config parameter, you can simulate the rows and columns and the minimum amount of consecutive disks. So all of that is customizable.
Got it. And there's a couple more questions. This game environment, is that built by Kaggle?
Yeah, Kaggle provides the game environment.
Got it. One last question, if you go back to that games obs.board. So I was playing around with it a little bit. So it's a list of 42 items, correct?
Yes. Yeah.
What I was not able to understand, and maybe this is the way that the game engine was built, you have in your agent definition, you're looking at observation.board index column. If you scroll up a little bit in your agent definition. Yeah, so you have obs board column index, and that column index only goes from 0 to 6.
Which line are you referring to?
The valid moves one for the random agent, for example, or the leftmost agent, doesn't matter.
Yeah, for the
So you have your column ranging from 0 to 6 because you only have 7 columns.
Yes.
And then you're checking if the board position for that column is 0, meaning it's not occupied.
Yeah. So the list starts from top to bottom. So you only check this 7 starting zeros to make sure. So this part, if observation board column is empty, refers to this first seven elements of the list.
Got it.
Because if they are not empty, you cannot drop a disk there. So if you're forced to drop the disk at a occupied column, you lose. That's why the agent always checks if the column is available before dropping the disk.
So basically, are you always checking if the first row is not occupied or not? Is that the basic check you're doing?
Well, when you play the game, some of the columns become occupied, as you saw, right? Like for example, if the agent plays leftmost, so it piles the first column, and then when it's full, it's forced to play the second column because it can't drop in the first column anymore, because the first element becomes 1 or 2. And so this first column is, or 0th column is already occupied.
Yeah, my point was that instead of just looking at the first row, wouldn't you look at all the rows in your game and then make a decision? That's more of a complex search.
Yeah, that's of course. Yeah, we'll build a more sophisticated agent. So as I said, these agents are just starter agent, just to illustrate that you can create basically any rule as to where you want to place the disk.
Got it.
But,
I was very surprised by that very simple rule that you're only looking at the first row, and it has 42 elements, but you're only looking at the very first 7 elements of the list.
No, but
Well, you should note
this thing will be applicable to all of the agents, because the valid moves tells you where you cannot drop the disk, basically. If it's occupied, you just, whatever your policy is, you can't drop the disk in the column that is already full.
That makes sense. Robert,
I had one quick question.
I was just going to basically clarify that the reason you can get away with only checking the top row is that the disk will automatically fall to any open slot. So the only way, if the top row has a disk in it, that means the whole row is full.
Got it.
Yeah.
Sorry,
exactly.
Neil?
Just a quick question. Do you know at the bottom there, it was doing the simulation of the gameplay by simulating the agents and giving you the percentage of winning?
Mm-hmm.
Do you know? I didn't see this. Do you know how many games it actually plays?
Yeah, there's a code there. If you just expand that, Dimitri. Scroll up.
Say again?
Scroll up.
I think it's 100. Like, for some reason, they're showing it as a percentage for the first 2 rows and a count for the last 2 rows. But if you multiply the first 2 rows by 100,
scroll up a little bit more.
Okay, 100.
There you go. There's a code.
That makes
right there.
Oh yeah, here, right, exactly, yeah. Number of rounds, 100. Yeah.
Oh, cool. All right, I was just curious.
Yeah.
Thanks.
Yeah.
Cool. Thank you, Dimitri.
Sure. So let me make sure that I'm in the right place. Yeah. So basically, the first step to make a smarter agent is actually checking if the next move will actually win. So a very simple one-step sort of look ahead strategy would be to see if the move actually wins, play that move. And so let me go down. Yeah. So we define a couple helper functions here. Basically, we define this grid object, and grid is basically a reshaped board into 6x7, just to be easier to check whether diagonals and then rows and then columns can win. So nothing interesting here. So drop piece basically takes an existing grid, takes the column that you want to play, takes your piece, so all of these arguments, and returns a new grid with your move. Basically, that's all it does. And then this is already interesting. So check winning moves. Check winning move basically tells you if the move that you're gonna make actually wins you a game. And so they take the observations, and then as you can see, the grid is basically the reshaped observations into 6x7. So the observations, the config, and the column that you want to place, and your piece, and it tells you if if any of the horizontal, vertical, or diagonal configurations are achieved. And again, I think it doesn't probably make sense to go through the entire Python code, but it's pretty simple stuff. And so the first agent, the Q1, is actually doing exactly that. So again, as I said, this thing is present in all of the agents. So to filter out the invalid moves, and then within the valid moves, we go through each of the column in the valid moves, and we check if any of them are winning move. And so if yes, we just return the column. So that's the whole agent. And remember, agent takes 2 arguments, the observation and the config, and returns the move, basically the column. That's just for clarity. This is the only thing that actually our interactions with this environment is only through the column, because that's the only sort of variable that we control. And if there are no winning moves, so if there are no winning moves, we return just a random choice. So if we don't see an immediate win the next move, we just drop at random. That's basically all this agent does. Yeah, it's so not spending too much time on that. The second iteration of that same agent is not only see if you can move next time at the next turn, if you can win at the next turn, but check if the opponent can win at the next turn. And so first you check if you can win, and if yes, you play. And then you check if the opponent can win by dropping somewhere. And then if yes, preclude it from happening. So, basically drop the same, drop your disk in that, dangerous slot. So that's all it does. Yeah, basically this is the Q2. Again, check the valid moves. First, check if you have the winning move, and then check if the opponent has any winning moves. And so, the opponent plays with a 1 or 2 depending on the configuration. So that's your mark. So basically, that's your color of the disk, and that's your opponent's disks basically. And so if the opponent has, if you have a valid move played, if not, check the opponent, and then also play. And if neither of those cases are true, again pick a column at random. So that's all it does. And I think for this one, yeah, we have the simulation. Let me, yeah. So if you're gonna create your own agent, just make sure that all of the imports and helper functions are within the agent, because we actually submit a full Python code to the competition. So your submission should be a self-contained Python function that takes these 2 arguments and produces the column. And that cost me like about 10 minutes figuring out, because I had definitions and imports in different places. It produced an error, and then I figured out it has to be a single block of code. Yeah, so that's actually we can play this agent, like we will play here. So the opponent is playing, K is the agent that you created. So if I play here, the K will place here, right? So to prevent me from putting here. And then, I can do this. Basically, okay, so it basically precluded me from dropping here. So it does work. And so that's basically the second agent that we submitted to the competition. One interesting module that was new to me is called inspect. Is actually, it has this get source method that lets you basically save the content of a Python function in a text file. And so that's what you use to actually save your basically the method, the agent, save it as a Python file, and then submit that file to the competition. So this inspect is interesting, and it has all kinds of different modules, all kinds of different methods and attributes. So if you have time, just check this out. So basically, we submitted that, and let me see how it's doing actually. So yeah, so that's the first. So that's the first agent I created. So yeah, its score is 686. I don't remember, what's exactly that score is. I think it's an average score of win-lose ratios, basically, when playing against the other agents. But that's what it gets. Yeah.
Actually, it's a clarification question. I'm receiving the same error message when I submit the file, and I see also in your case.
Yeah.
So, do you have anything to say about that? I don't know. I want to learn.
So those errors, those errors were exactly the result of the Python file not being self-contained Python file. So it has to be like a Python, basically a module, right? So all the imports in the same function, and all the helper functions within the same function, and then that function is able to play against the others. If it's in different cells and you import something before, and then the helper functions are in different cells, etc., it doesn't work. So everything needs to be in one block of code. That might be the reason. There probably could be other reasons why, like for example, the arguments and the return values are not in compliance with their requirements, but my errors were because of that.
Question regarding the competition: are you playing against a specific Kaggle opponent, like a very specific version of it?
No, they match all the participants against each other.
Oh, really? Oh, wow.
Yeah. It's an environment. They explained the scoring somewhere, but it didn't make much sense. It's only basically only the relative score matters.
So you randomly paired up with other players and you play against.
Yes, yeah, that's how they describe it. Yeah.
Oh man, so if you paired up with a player,
and they actually will continuously evaluate your agent against other agents over time.
Yeah. The scores have changed since I posted them a few days ago, probably 3-4 days ago, and there is some evolution. So they continue to match that agent against the others.
Does it mean your score will get lower and lower over time then?
No, it's stabilized. So that I don't remember what happened actually. The first, basically, when you first submit it, it's very unstable, but then within a few hours it becomes stable.
Got it.
So these agents that we just saw, they don't have basically any brains, right? So the only thing they check if they can win at the next step. So a slightly more involved version is actually trying to understand what would happen, one or two steps or n steps ahead. And basically a concept that helps us sort of understand the game development is called the game tree. In this particular case, the trees are pretty simple, unless the top row is occupied. So while the valid moves are all 7 columns, each next board produces 7 possible combinations, and so the opponents play consecutively. It quickly gets out of control, right? So 7, it's basically powers of 7 every time, and so we can't actually count on covering this tree to any meaningful depth. And as I said, there are 4 trillion combinations, but we can at least see maybe what happens one step or a couple steps ahead. And so another concept that they introduce, and actually we will use that in our agent, is called Heuristic Function, which is basically in contrast to game theory or full reinforcement learning reward which basically is your typically your cumulative reward across through the entire game, right? So here we don't have that luxury to calculating or somehow discounting that, which they do in modern software, right? When you play chess or Go, it's very complex functions that go as far into the future as possible. Here we have some very limited understanding of what's good, probably maybe one move ahead, and so this is more like a value function that describes basically in a very simple terms how good or how bad would be your next move. And these numbers are completely arbitrary. So basically what they do is assign a numerical weight, right? Numerical value to your next move or to any position, basically. So they you would get 1,000,000 points if your next move produces you a win. You would get 1 point if your next move produces filled 3 spots. So basically, this is the, let me make this larger. This is the ideal situation. This is the 3 spots, and so these create the opportunity for you to win at the next stage, at the next step, right? And this is a very dangerous situation because that's the opponent creating an opportunity for itself. And so basically, whatever configuration you have now, basically you try to imagine all the possible 7 configurations, 7 grids at the next step, and assign each of these 7 possibilities a score based on this scoring sort of principles. Of course, if any of the 7 has this 1,000,000 points, basically if any of the 7 is a winning configuration, you play that. If not, you play one of these. And so the logic is very simple. You play the configuration that maximizes your total score. And so they have this example. And so in this case, if this is your starting board, if you play the leftmost column, you have a fork here, right? So you create an opportunity for you to move to win at the next stage, at the next step. And so this is the optimal play. And all of the others are inferior. So that's basically the logic they follow, and we'll create exactly that in the next just hold on a second.
When you search for these patterns, are you searching only horizontally, vertically, or also diagonally?
Diagonally too, yeah.
Okay.
So you search everything. Let me skip this and go directly to my notebook, because we repeat this and we do actually something more. So so we basically build this agent that calculates how many 3s, 4s in the row we get. Oops, hold on a second. Yeah, so how many 2s, 3s, and 4s we can get, and how many 2s and 3s the opponent can get. So that's a slightly more complex version of what we saw, because we added the 2s. So this is basically an opportunity for us to win in 2 moves. If the opponent is stupid and doesn't see this, right, or the opponent is random, then this creates an opportunity for us to win in 2 steps. And so this is also valuable. And the 2 here, the D, is again a danger for us in 2 steps. So E is a danger for us in 1 step, and D is a danger for us in 2 steps. And so what we do is basically we assign a numeric value to each of these configurations. This is the A, of course, is the best, and then we can we go down and basically assign a numeric value to this. They have a suggestion here. Yeah. So basically, I followed their suggestions. The A is some very, very large number, and then 10,000, 100, -1, and minus 10,000. And I've seen people played with this. So you can imagine different configurations. It was just designing the best reward structure was not the point of my exercise, so I didn't play with them. I just took them as suggested. So
do you think that will make a big difference? I mean, I understand that as long as there's a difference, like
they should, yeah.
It should?
Yeah, they should.
So if you multiplied every score by 2, the relative difference is the same. I would expect the performance to be the same, but I don't know.
Yeah.
Could you copy that cell and run that? I'm really curious to see if that makes a difference.
Sure.
It would take it would just take a second to do. Well, because I want to retain the original win percentages, but so it's like 0.58 for the agent. Yeah. Because I guess my theory is that the relative rewards are probably more important than the exact numbers.
Of course, yeah. No, that goes, yeah, of course. So multiplying, or
and then
probably.
And then I've wondered if A was like 2 to the 6th, would that still win? Or if A is 2 to the 8, would that still be the same?
I think I think A needs to be much more than any of the other alternatives. Yeah.
I think the point is that like none of the others combined can beat A. Like
yes,
A will.
I think it could be exactly. Yeah. So
I guess
that's the
6 or
design
something.
principle for this entire set of selections, right? No one can beat the next one greater than it. So if you have a single E, that's each one is 2 orders of magnitude different from the other one.
Right.
So just a single instance of one thing can dominate even if you have 4 instances of B.
Right. So if you have A dominates everything else, and for example E is more dangerous than B. So if they have basically if there is any E, your objective is to kill the opponent's E as opposed to create a B for yourself. So if you have something like this, if you don't have any A's but you have E's, your priority is to kill the E's as opposed to create anything for yourself. So because it's rare that you have like more than couple or maybe 3 combinations per next game, per next step. So I think even 1 order of magnitude of difference would do. So if they're 1 order of magnitude apart, that would already produce the same results. Just let me, in the interest of time, skip all of that. And so yes, so this is the agent we create. Basically, what we need is to score our next move, right? According to this scores that we created, to these weights. And so we need to create this get heuristic function that would evaluate the next grid. Remember, next grid is the grid after our move, and then basically return it to this agent so that it can compare the one move to the other. And so the get heuristic basically multiplies this weights by the number of 2s, 3s, 4s, and the opponent's opportunities. So and basically the cumulative score, as we just discussed, it weights this according to these numbers, and these numbers, the number of basically the number of combinations is calculated by a count windows, by this helper function here, which goes through the entire grid and counts how many of that empty opportunities you have horizontally, vertically, and diagonally. Basically the agent body is again checking the valid moves, creating the grid, and basically assigning the score to each of the columns that we can play, and selecting the column or the columns that have the maximum scores, and then playing randomly any of the columns. So let me know if there are any questions so far. Okay. So basically, once we create this agent, we can go ahead and play it. And this one is already quite a clever player, actually. I tried to play some with it. It does actually play good moves. For example, I'm not following the game right now, but for example, I can't select the middle column right now, because if I do here, that's there he won. So it already takes some concentration, not to make a mistake and play against this agent. And again, I submitted that, and that was the second one, probably 700 or something. Let me see.
I find it interesting when you develop an agent that you cannot beat yourself.
Say again?
I found that interesting that you develop an agent that you cannot beat yourself.
Yeah. The multi-step look ahead is a really tough one. So let me. Can you see my screen?
Yes.
Yeah. So, but that was just one step ahead, right? So we waited and basically compared different configurations just one step ahead. What would happen if I played the next move?
So did they give you a better score in the competition than the previous one?
Yeah. So just
so you jumped from 600
from 700 to 860. So that was the difference. So the agents we just discussed were capable of looking ahead just one step, and here in this section they describe an agent that is able actually to look ahead for a few steps to decide what the best strategy is, and they bring an example of why multi-step strategy is better. If this is the board we start with, let me make it slightly larger. So the one step ahead strategy would rank these two columns. So the column 5 and column 6, they will rank equally, but actually column 5 is a bad move, because if we drop the red disk here, the next move is a winning move for the yellows. But our agent doesn't know that, because it can only look one step ahead into the future. So obviously, the deeper the agent can look into the future, the better it can play. And we could imagine, the ideal agent would look, 21 steps. So because each player gets 21 steps, so 21 steps into the future, and build, this ideal map the entire tree of the game. But of course, even in the simple case of Connect 4, this is computationally infeasible. So we need to come up with some sort of intermediate solution. And what they describe here is 3-step look ahead. So what we actually will build a tree for and evaluate is 3 steps: agents move, opponents move, and agents move once again. So this is a 3-step look ahead tree. This is a binary tree, but in Connect 4, as we saw, there are 7 possible columns. So this is 7 cube leaf nodes at the bottom, which is, it's a quite reasonable number, easy to evaluate. And the approach with which we will evaluate, which column to play is called Minimax, which is a well-known classic algorithm in game theory, describing the decision rule that you follow to maximize your gains, given that you think that the opponent will also play optimal and try to minimize your reward. There's a ton of description online, including Wikipedia. Let me give you just a brief overview of how it works. Basically, Minimax is a decision rule that lets you pick a strategy that gives you a guaranteed minimum reward. So you're protecting your odds in a way. So, for example, for this tree, they have a nice example here. So we play the reds, and the opponent plays the yellows, and so these are the final rewards that we will calculate. Actually, the algorithm will calculate the reward for each of those 7 cube leaf nodes. But then the Minimax algorithm tells you which path to take to actually squeeze out the maximum reward for you. And so if we look at the leaf nodes, of course, when we are at this second to the last level, we will choose the best reward for us. So if we're here, we will choose this 40 and -1 as opposed to -20, +10, plus 30. So these are our choices. Now our opponent also knows that, so we assume that it's a rational opponent, and so because of that, the opponent will actually push us to the lowest reward possible. So this is the min part in the min-max. So if the opponent is here, he or she will push us here and make us choose the -1 branch. And so if the opponent is here, he or she has the choice between +10 and +30, so it will push us here, and so we'll get +10. And then finally, at the top of the tree, we basically have the choice between -1 and 10, and so we will pick the +10. So in other words, when we're here, we are guaranteed to have the +10 reward. From all these, possible rewards at the bottom, this is the maximum of the minimums that the opponent will allow us. So that's the essence of the Minimax. Let me skip the code here and go directly to the exercise, because the exercise is describing pretty much the same Minimax algorithm. Okay. So, yeah, they describe different reward structure. This is along the same lines that we have already seen. Okay. So here they ask the question of how many leaf nodes that there would be in our Connect 4 game. And so, for this binary tree, it's of course, 2 to the power of 3. For the Connect 4 game, each player has 7 possible opportunities. So it's 7 to the power of 3. Here they, are asking us to basically emulate the Minimax algorithm. And so basically they're asking, how much, or what is our Minimax reward for here? And so basically the opponent will pick the worst reward for us, right? So here it will make us pick the +1. So this is +1. Here they will make us pick the worst -80, -80, and -100. And so we will choose among -100, -80, and +1. And so we will pick the +1. So our Minimax reward here is +1, of course. So this is an interesting question about whether the same Minimax logic or Minimax decision rule should be applicable even if we relax the assumption that the opponent plays optimally. So if, in other words, if the opponent makes mistakes, is the Minimax algorithm still applicable? And the answer is yes. So it's the optimal decision rule for both, for any kind of situation. And if the opponent plays suboptimally, what you end up with is maybe unexpectedly better rewards than Minimax. So Minimax provides you the lower bound. It's the guaranteed reward that you get, and if opponent makes mistakes, your reward might be even better. Okay, so let's go to the agent itself. And so many of the helper functions are the same that we have already seen. The score move that gets you the actual reward for each of your possible scores, possible moves. The drop piece that recreates, the next board. The count windows that, checks how many combinations you have at the next move. The same get heuristics. There are some new ones, like checking if the next move actually produces a terminal node. So if it reaches the depth that you specify. But the interesting part is the Minimax itself. And so Minimax is, let me make it larger. So Minimax is a recursive function that calls itself recursively. Here is one Minimax, and here is the other. Calls itself recursively to go through the stages or the depth of the tree. And so basically how it works is maximizing player is the agent and minimizing player is the opponent. So if it's the maximizing player's turn, it goes through all available valid moves and then creates the child boards for each possible move, and then selects the maximum reward from whatever the opponent will allow it to get. So the opponent is working the other way, right? So the opponent minimizes the reward, and this is the opponent playing. So when it's false, is the opponent. When it's true, it's the agent. And so the opponent tries to minimize your reward, and the agent, knowing that, selects the maximum value that the opponent would let us get. And so the same logic works for the opponent. So when it's the opponent turn, it minimizes the value that we are maximizing, and so basically it selects the minimum of our maximums, as we saw in the picture. So that's basically the whole logic of how it works, and it actually fares pretty well in the competition. And if you play it live, it actually it's quite difficult to beat, even at this depth 3. All right, so Alexandra, should we move into deep reinforcement learning.
Just before we do that, so that one gives you the highest score so far in the competition?
Yeah.
Got it.
Yeah, it gives 933. So.
And if you click on that episode's view, it shows you a screenshot of your game. Is that what it is?
Yeah. It plays against the others. So these are the other agents, basically.
Click on one of them just for curiosity. Yeah. Oh, you're the blue one. Got it. Oof! Look at that game, Dimitri. This is just one game, I guess, huh? Okay.
Yeah. And it plays, oh yeah, here it is. So 28 minutes ago, 6 hours ago, 10 hours ago. So it plays all the time.
So you always win? Oh, sometimes you're losing, I guess, right? Got it.
Yeah. Like,
all right.
So.
And that 1034 there is the opponent's total score across all the games that they've been simulated for?
Must be, yeah.
Oh wow.
Because this is mine, and
but look at that, he wanted the
I'm curious now that we see a completely full board that the was won on the last turn. Is it a draw if the board finishes with no
yes, yeah, it's a draw, yeah.
Or is it a loss for the person that would
no, it's a draw. It's a draw. Yeah.
So 0 points for both, or 1 point for each?
Say again?
Is it, do you get any points or no?
Not sure how it's calculated. And actually, you know, the optimal player, so if the first move is here, so the third or fifth column, it's guaranteed to be a draw if both opponents play optimally. So the central column is guaranteed win, the edges are guaranteed loss, and this is guaranteed draw if both are optimal players.
I have a question here. So
sure.
When you start a game, don't you have an advantage? So let's say you started and the opponent second, and then there's a draw. Is it unfair for the opponent? Maybe you should play also another game in which he starts, because whomever starts first have obviously advantage.
I'm not sure how the simulation is structured. I would assume it must be at random who starts.
Still unfair though. Okay.
The one before this in the exercise, I think half the times you were starting, half the times the other opponent was starting, just for that reason, I think.
So you play more than one then? Okay.
Yeah, the exercise. In the competition, though, it looks like you're only playing one game against a random player, and randomly gets assigned maybe.
Well, but yeah, if there are enough games and enough components in the same sort of within the same rank, then it sort of averages out. Yeah.
Yeah, maybe instead of random, you start one game and then you be second in the next game or something.
But it's interesting. You're saying, is there a statistical difference if you start first? Starting first doesn't give you a statistical difference in terms of winning or no in this game?
Yes, yeah. Starting first, if you start first and start in the center, and you build like N lookahead agent that can can evaluate like 21 moves ahead, you're guaranteed to win, basically.
Similar to tic-tac-toe, I guess.
Yeah.
Yeah, I was silly question, but I was wondering like if you can play optimally and be guaranteed to win, so then if you are the first move and you can play optimally, then you can always win. So how hard is it to play optimally? Do you really have to look 25 moves ahead, or is there some strategy you can play to do that?
Well, one strategy would be to look, as many moves ahead as computationally feasible. Like, I'm sure, even with this, you can build like maybe 3 or 4 or 6 or 8 moves ahead strategy, because it's basically powers of 7, right? It's not astronomical. But then maybe, there are all kinds of heuristics, right, in this game. So the number of forks or like, opportunities in different directions, etc. So, you could, if you spend time, I think you could come up with pretty good heuristics to basically assign value or reward, associated with different moves. But brute force 4 trillion configurations, yeah, I don't think that's a feasible thing.
So is it just that some mathematician figured out that it's a solvable game and they didn't actually solve it? They just proved that it could be solved? Or did somebody actually, at some point, actually write an algorithm that can win this game every time if you get the first move?
The latter, yeah. Actually, there is a full sort of the optimal game ends in a particular configuration for the first player. So there is a very specific configuration. What happens if both are gods, basically? What happens if they play? And the first god always wins. Yeah.
Christine is asking, did you do any other optimizations in your last submission, or just the n=3 look ahead?
No, just n=3 look ahead.
Okay, thank you.
Yeah.
Cool.
I was looking forward for the deep reinforcement part, and that's why I didn't spend much time trying to tweak and do all kinds of things here. Just reproduce what they have, basically.
Sure. Awesome.
Also, can I ask another question, actually? So given that you find the best algorithm, as we discussed, like that always wins if it starts first, in that case, does those numbers that we gave as weights for better options matter at all? Like, do you remember we did like 1 e to 10, 1 e to 6?
Yeah.
And like also another question is that since we are trying to optimize those numbers too, can we make a simple another reinforcement learning algorithm that simply gives us the best weights that works for that problem?
Well, the first question, these rewards are very rough estimate of how good the configurations are, right? They don't even attempt to connect it to the final reward. So it's not a reinforcement learning problem per se, right? When you have like the full run and then the signal propagates back, that there is no learning component here. It's just a heuristic that we sort of give it basically out of blue, just because we think 3 in a row is better than 2 in a row, etc. And so whether that simple rule can lead to optimal strategy, well, I would think no, but that's a very separate question, and you would have to explore how good your heuristic rule is, basically, right? So these are very, very simple sort of policies. It's not optimized for the purpose of winning the entire game.
I find this competition very interesting, fascinating, because you're constantly competing against each other, against other players.
Right. And I'll find the edits that I did, and I'll post it on Slack. Okay, as I said.
Cool, thank you. David is saying that Connect 4 is mathematically solvable game, and there's a solution. Okay. I wonder how complex it is. Cool. Thank you, Dimitri. That was awesome. Alexandra, the floor is yours. Looking forward for some new strategies how to tackle this interesting competition.
All right, thank you. Let me share my screen. And we will dive into deep reinforcement learning. So I think one of the cool things about Connect 4 is that because we can understand it really well, it's a nice toy problem for what I find really interesting is using deep models to do reinforcement learning. So instead of like hand designing a heuristic, which can work and can be very effective, some problems that perhaps are too complex. And so perhaps you can have a deep learning model learn heuristics for you. So how does that work? So one thing they highlight here is that it's difficult to come up with a perfect heuristic. And it generally entails playing a game many times, like hand coding, like different heuristics and so on. It's hard to debug and so on. And then for more complex games where the decision or action space is much larger than, pick 1 of 7 columns, picking a good heuristic can start becoming very difficult and cumbersome to do by hand. So deep reinforcement learning is a way to do this automatically using gameplay experience. So the idea here is you give your neural network a game board as an input. So you give it this Connect 4 board and you pass it through your neural network and it outputs a probability for each possible move. And I hope you can, let me zoom in just a little bit so you can see this better. But here it gives you different probabilities for selecting each column. So column 0, you have the 0%, or sorry, a 10% probability of selecting that column. Columns 1 through 3, no probability of selecting those columns. Column 4, 50% probability, and so on. And so then your agent would select a move by sampling from these probabilities. So for the game above, your agent would select column 4 with the 50% probability, and column 6 with the 35% probability. And so then to train your network, you then have your network play a lot of games. So how do you set this up? So the first thing you need to do is you need to give an agent a reward after each move, and this tells it how well it did. So in this system, they define the rewards slightly differently than before. So first, if the agent wins the game in a given move, you get a reward of 1. Otherwise, if the agent plays an invalid move, you get a -10. If the opponent wins the game in the next move, so your agent failed to block the win, the agent gets a -1 reward. Otherwise, the agent gets a reward of 1/42, which is, I'm not sure why they picked that specific small number. One thing to point out is that like the largest negative score is if you play an invalid move. So we're really making sure that our agent knows to not play invalid moves. So then at the end of each game, your agent will add up its reward. And this will be called the cumulative reward. So if your game lasted 8 moves and your player played 4 times, then your cumulative reward is 3 times the reward you get for like just making a move, and you add 1 for winning. So this is different from like the Minimax algorithm, where in Minimax you got reward for 3 in a row, 2 in a row, and so on. This is a lot less structured, and you're not trying to push your agent in one way or another. You're just saying, hey, we really want you to win. Don't lose. Don't play an invalid move. And it's good to keep playing. They say somewhere that this 1/42 reward for just playing is important for convergence of the algorithm. So we use that. And one thing they say here is a key aspect of reinforcement learning, a key challenge is tracking rewards to track the performance of an agent, and then setting up the problem properly, I think, is also very important.
Alexander, sorry to interrupt. There's just a couple of interesting comments in the chat. One is that there's 42 slots or places on the board, which is 7. So that's probably worth it.
Oh, okay. That's a good point.
There's a question about what is an invalid move, and I was maybe thinking you could answer that.
Sure. An invalid move, it would be, say this column were full and you try and put another token on top of it. That would be invalid. So you can't, if the column is full, you can't put another token on top. That's invalid. So if you try and do that, well, the game is lost. I think in other simulations, like if there were an edge, you wouldn't want to take a step off the edge. So you wouldn't want to like place a token over here or place a token over here. That's not really given as an option, but there's other reinforcement learning environments where that's possible. Are there any other questions?
No.
Okay, cool. So there are a lot of different reinforcement learning algorithms, and they list a few here. And these are well known. And all of them use a similar process to produce an agent. So they start with a neural network initialized with random weights. And then as the agent, so your neural network, plays a game, and by playing a game, the neural network takes in that game board, passes it through the network, and then predicts or gives you a probability of, you know, which place to place the token. So as the agent plays the game, the algorithm will continually try and, you know, reevaluate the network, update the weights to see how the reward is affected on average, and then update those weights. And so then after a lot of gameplay, the weights should start to converge to something that maximizes that cumulative reward. So this way, the agent will try to win the game, so it gets a final reward of +1, avoiding losing for the -1 reward, and avoiding the invalid moves. It also tries to make the game last as long as possible, so it gains that little bonus points as many times as possible. Oh, and here, this is where they discuss, like, hey, like, why do we want to do that? And they say it makes it converge better, and you can read about it in more depth via the temporal credit assignment problem and reward shaping. And so there's various research on like reward engineering. So that's kind of what we were discussing before. So do you give a +1 reward when you win, a million reward when you win, and so on? That's in this area about rewards shaping. So are there any questions?
I had a comment on that, which I found kind of interesting. One thing I noticed, I really hadn't played this game at all since I was probably 8 years old or something. And I noticed when trying to play against my own agents, especially the N-Step Lookahead one, when I won, it tended to be in fewer moves. Like my strength against the agent was in strategizing at the beginning of the game and really drawing a strong position, like opening the game well. Its strengths against me, I think, were in the end game when there were fewer total things to consider. It was able to be more exhaustive. So I wonder if the 1/42 bonus, like drawing it into the end game, is somewhat helpful as far as just the fact that a strong agent is likelier to win the longer the game goes. I just thought of that while doing this. I was wondering if anyone had any thoughts on that.
Well, maybe it also incentivizes the agent to build that strong foundation if it can figure out how to do that. So kind of what you're doing, but like giving it the time to learn to do that.
Yeah, I was wondering if, you know, like more pieces on the table, more chances to put 4 in a row.
That makes sense. A couple more questions. Alexandra, Neil is asking, when you're training this agent, who are you playing against? You're playing against another random?
Yeah, so you can specify who to train it against. And you'll see this in the code. The code has you playing against a random agent, but you can change who you play against. And I'll show that as I go through the exercise at the very end.
Sure. One more question then. When you convert the board state to an input to your neural network, is that just a simple like matrix to vector representation? Is there any heuristics you can apply there? Basically, a better encoding gives you more advantage or better advantage? I'm curious.
I think the idea is that the network figures that out. So if I remember correctly, and we'll see this in a second, but I think you pass in a matrix to a convolutional neural network, and so the CNN can, you know, try and do some low-level encoding to do a better prediction. So you're basically pushing off that encoding to the network and hoping the network figures it out.
Can I ask one question? So even though like when you do a neural network and it works perfectly good, still it will heavily depend on your initial like first move, right? So how do you decide first move? Or like weights that you did in the first part?
So my thought has based on the previous discussion is to amend a network agent with some simple heuristics, like you're going to do better if you start in the middle, and you're guaranteed to lose if you start on the edges. So just take that, do that first move deterministically, and then let your agent do the rest. I might try submitting that actually.
Like a bootstrap network.
Yeah, I was thinking like if you try to do a plus sign in the middle, in the center of the board, it's probably the best option because you are closing all of the four, like it can be diagonal or like row wise, column wise. But obviously it's not only your choice, because depending on other opponent's choice, you can put those points, and it probably also would delay the game, which will eventually give you more points. Rather than trying to win directly, maybe trying not to lose first, and then since you have last move if you start first, it might be a better option. But when you start second, then it's not gonna work well.
Yeah, I mean, I still think that's a nice slight advantage that you can give your agent. If there's not any more questions, let's go on to the code, which I think will help make things more clear. So there are a number of implementations of these reinforcement learning algorithms in different Python packages. Here they use the stable baselines package. And they note that it's not yet compatible with TensorFlow 2, so they do some stuff with TensorFlow 1. And then, so the environment that we used in the previous lessons isn't compatible with stable baselines. So they do a little bit of extra work to create a Connect for Gym. And this is based off of the OpenAI Gym environment. So a little background, OpenAI is, a AI company, and they have this Gym software package for reinforcement learning. So their Gym package has all sorts of reinforcement learning environments already loaded into it. And so you could just load up a pre-built environment and train an agent to, perform whatever task in that environment from this OpenAI Gym. Here, the code will create this Connect for Gym environment in this OpenAI Gym syntax. So they built a class for this gym with a couple of functions. So there's a reset function that just resets the board. There's a function for changing the reward. So this allows you to customize the reward that the agent receives. And then most importantly, there's a step function. And this is used to actually play the agent's chosen action in the environment. And step returns a couple different things. So it returns the resulting game board from the agent's action. It returns the reward from that action, and it tells you whether or not the game is ended. And this is important to know. And there's documentation around how to define environments for the stable baselines reinforcement learning package. So here we have the Connect for Gym. So we initialize it with a Connect for environment. And so we're just making an environment like we did before from Kaggle. We're setting that, and in this environment, we're having it do some training. So when you set up your gym, you could set your agent 2 that you're training your agent against as random. You could set it as something else that's been built in, or you could actually train your agents against each other, which I did, which is fun. Let's see. There's a couple other items that are set. The OpenAI gem and stable baselines requires your action space to be set and your observation space to be set. So your action space is basically each column number. So there are 7 columns, so your action space is 0 through 7. And so you just have to set that. Your observation space is basically a matrix of your game board. And these are concepts that are pretty big in reinforcement learning, and they have you specifically define those here. You need to give it a reward range, so your min and max reward, and then a couple of things that stable baselines requires. Here we just reset the board, simple enough. Change reward, simple enough. And then the step function basically passes in the action from the agent and gives you a new game board, as I said before. So in this notebook, you're training an agent to be a random agent, and you specify your opponent below. So here we create connect for gym environment, and we specify that our agent 2 is just random. Stable baselines requires us to work with a vectorized environment. And so a vectorized environment basically allows you to run multiple games at once, but each game is like a different element in a vector. And so by vectorizing it, it's quite fast to run multiple games at once. And so this helps speed up the training of the agent. There's also a monitor class that we have to use, and this lets us watch how the agent performance changes over time. It says gradually improves, but I'll show you why I laugh at that as it plays more games. So here's some sample code. We import monitor and the vectorizer, and we set up the monitor environment object. It takes in the environment, which is the Connect4 gym, the folder where we want to save the monitoring stuff, and another parameter. We also set up a vectorized environment, so the vectorizer class, and we just give it the monitor right here. So the next step is to specify the architecture of the network. And they use a convolutional network, though you could also use just a dense, fully connected network as well, and see whichever works best. And in this example, they use the PPO algorithm, which they don't explain in this tutorial. We're just taking these reinforcement learning algorithms out of the box. And there's plenty of places where you can read more about these sort of reinforcement learning algorithms. The key point is that PPO is an algorithm for training your neural network to do reinforcement learning. And it's cool that it is not hard to do in code. So here we have a function to build a CNN. Let me keep the imports because I think they're helpful. So for the modified CNN, we passed in scaled image, which I think is just the matrix from the Connect4 board. We give it an activation function. We have 2 layers, and we have a convolutional layer with filters and strides and so on. And then we pass it through the activation, and then we have layer 2 with another convolutional layer. And then we pass that to a fully connected layer, and then we return the probabilities from the fully connected layer. What's worth highlighting is the only thing that's actually from TensorFlow in this code is the ReLU function. The rest is actually utilities from stable baselines. So this network is not primarily a TensorFlow network, it looks like, but utilities from stable baselines. I'm not sure it matters a ton. The last piece is there's a CNN policy within stable baselines, and we customize it with our modified CNN. So
are you treating the game state as an image then? Is that why you're using convolutional networks here?
It's a 2-dimensional matrix. So you can take a kernel and slide it across. And so you can take your kernel and slide it across your matrix. An image is just a matrix as well. Mm-hmm. I'm not sure why they call it a scaled image.
Okay.
But yeah, I mean, you can use a CNN for anything that's like a two-dimensional matrix, or, you know, a series. Are there any questions about the definition of this network? It's just a two-layer convolutional neural network with 32 filters on the first layer and 64 filters on the second.
No, I don't see any questions, Alexandra.
Okay. So in the code cell above, the weights are, of course, randomly initialized. And then in the next cell, we will train our agent, which is done via the PPO algorithm in this case. And so we just take this model that we initialized and we do model.learn. So model, again, came from model equals PPO of the custom policy in the vectorized environment. And we just do model.learn, and we do it for 100,000 time steps, and we plot out the rolling average cumulative reward. So you see at the beginning, its cumulative reward is awful. It loses all the time, takes all sorts of invalid moves, and then over time, it learns to win. And then, of course, you can submit this agent for the competition. So let's jump over to the code. Oh, I guess one last thing that's worth highlighting. They discuss the idea of self-play. So self-play is a cool idea where you have agents just play against each other. So instead of playing against a random agent, you have different agents learning how to like do interesting things just by, you know, playing around. And so I encourage you to click on this link and check it out, because there's some cool images of what agents have learned to do via self-play. So maybe like this one. But yeah, the point is that like over time, these agents learn to do more without any guidance or any heuristics. They just figure it out based off of the rules of the game, which I think is pretty cool. The other thing to highlight at the very end is they list a number of resources to learn more about reinforcement learning. I haven't looked at David Silver's videos, but they look interesting. I've read a couple chapters of the Sutton and Bartow textbook on reinforcement learning. It's a classic. The one caveat is that it doesn't do any deep reinforcement learning. It's all classical, but it's still good foundation. And these also look like interesting resources as well. So let's jump over to the exercise, which I have loaded up here. So they have a couple of questions that they ask at the beginning. And I think these questions are interesting. So their first question is, say you wanted to create a neural network that can play chess. How many nodes should you put in the output layer? So you take in a chess game board with the pieces where they're located. How many nodes should your network predict each move as your possible options?
I noticed in the tutorial they had used 512 on that last dense layer, and I was going to ask you why they chose that. It might help answer this question.
No, so I closed that tab, but I honestly didn't pay attention to the exact architecture. But 512 is divisible by 2, so it's probably memory optimal number. I don't know. I don't really know how they selected their architecture number of layers.
Okay.
Yeah, I was wondering the same thing, because I saw that and didn't recall seeing any softmax node or something that had 7 outputs, which you would think would be the final for something like this.
Right.
Yeah, they probably picked something that worked well enough. I'm scrolling down to see the same thing. Yeah, I see what you mean.
But it's possible that active of linear of something, that active is an activation, which is the value. So I don't know.
Yeah,
Maybe
it's
there
really
is
not a softmax. Yeah, I don't know. It could have something to do with stable baselines and stable baselines doing that softmax at the very end for you, because this neural network is, heavily integrated and defined by stable baselines. Like this con function is from stable baseline, as is this conv to fully connected. So
Yeah,
it's probably something to do with.
It's just automatically generated by stable baselines. Stable baselines knows enough about the rules, I guess, once you give it the configuration.
Yeah, that's my guess. I'd have to read the documentation. So going back to the question of like how many nodes should you output for a game for chess? Are there any guesses? Okay, I'll just go ahead. It would be C, which is the number of possible moves in chess. And apparently I didn't load something, so that's interesting. In any case, the answer is C. Oh, I didn't import this. Okay, that's fine. The answer is C. We're going to skip this section. It's talking about a different game. And then last, we're going to amend the code from the tutorial to build different agents. So here I do a little bit of experimentation with the Connect 4 environments using different deep reinforcement learning algorithms. So they have a set of 5 reinforcement learning algorithms that are implemented in stable baselines. And so in this experiment, I am going to try each one, see how it does, and pit them against each other, and then see how they do. I didn't have time to do more because each run took, I don't know, over 15 minutes. So it's pretty slow to, iterate on an agent, because we're training on 100,000 time steps each time. So here's how the PPO algorithm does. It slowly rises and gets close to 1. I actually ran this an earlier time, and it had some weird behavior where it seemed kind of unstable. It's worth highlighting that this agent is trained against the random agent, so perhaps that could make it more difficult to converge. Then I try all of the other reinforcement learning algorithms that they point out, just to see what happens. So the A2C agent seems to be doing really well, and then it hits some awful area in the network space and just does really bad for a long time. And then it eventually recovers a little bit, but it still does very poorly. I wonder if on a different run, it would perform differently. Or if I were training it not against a random agent, but a more intelligent agent, if it would have done better. Then there's the Acer algorithm. It also has a deep one point where it falls in the pit and eventually figures out how to play the game again. This other algorithm, same story. Sometimes it does well, sometimes it does poorly, depending on where we are in training. And same thing with the last one, TRPO. And I guess one thing that I find interesting is this instability in the network performance. And I don't know if that has to do with, how the network is being trained, if it has to do with the agent that it's being trained against, if it's due to the random agent. I don't really know. So I thought it would be interesting to then pit the final agents against, well, first the random agent. It should do better than the agent it was trained against 100,000 times. And so here we see PPO, generally does better, 82% win percentage, which is nice. Forget what the heuristics hit, but 82 seems nice. E2C only has a 59% win percentage, so that's not that great. Acer has the highest win percentage of all of them at 93%. And then there was some, I don't know why, but this algorithm seems to always play invalid plays at the point at which it stopped training. So that algorithm I did not consider further. And then the last algorithm, TRPO, seemed to be a little bit better than the random agent, but not that much better. I also pitted the agents against each other, but the performance against the random agent was a good indication of how they would perform against each other. Acer and PPO did the best against the random agent, but Acer seemed to do a lot better. So I decided to train Acer against the trained Acer, so sort of self-play. So I took the static Acer agent and trained a new model again, like new model Acer model from scratch. And so trained for a long time. I admit I just trained this an hour ago because I was curious what would happen. And the Acer, the original algorithm, lost against the self-play agent. So that's great. The self-play agent seemed to learn how to beat the original one. I also pitted the self-play agent against the random agent. So this is self-play, and self-play seems to be about the same against the random agent as the original agent. But so perhaps the random agent isn't a good baseline, but it's nice to see that it's not worse. Are there any questions? I ran a bunch of different simulations and combinations just to see what would happen. I didn't, try and tweak anything related to the network or the reward structure just due to time. But that's probably what I would toy with next. I think the cool thing was being able to easily apply these algorithms. And once you understand the syntax and the structure, it's easy to swap in one for another without necessarily understanding or needing to understand the details of the reinforcement learning algorithm. So I'm sure that could help.
Awesome. Thank you, Alexander. This is very useful. One quick question. I know that you trained for 100,000 time steps, but in your graphs, it only shows a subset of that. Is there a reason for that? Or is that some kind of averaging or windowing?
Yeah, it's a rolling window of size 1000. I accidentally pressed refresh instead of mute, my bad.
David was asking maybe you'd see a faster training time if you had an accelerator turned on, maybe a GPU or...
This is probably true. Yeah, I didn't try that out. I haven't spent too much time. Oh, lovely. Well, I'm glad I didn't press refresh earlier because I lost all of that information.
Now, if you click on that number 2, it says save version 2. Yeah, click on that and go to viewer. I think, so that's version 2. Sorry, I think if you choose version 1, you might be able to see it. If you go back. You have version 1 there, yep. You can scroll down, yeah.
Yeah, version 1 won't have the stuff that I just ran. Oh well. Let's see. I was just finished.
Like it was saved 1 hour ago, so maybe did we just look there?
Yeah, I was trying to save it and then I canceled the save and then the save didn't happen. So that's fine. I showed the important stuff. Oh well. I'm sorry I didn't get to submit that agent, but that's fine. I'll just rerun it.
Do you know if the 5 choices for the RL algorithms like Acer and all. Can you submit your own, or you're limited to the predefined defaults or whatever?
Not limited. I assume Stable Baselines has more than 5 reinforcement learning algorithms implemented. And the literature, I think, is quite deep. So, I mean, you don't have to use Stable Baselines either. You just need a model that can do a prediction in the required format.
Okay.
Can I ask 2 questions too?
Of course.
So like, since you're comparing these models and you already have an existent deep learning or convolutional neural network model that you feed into those, architecture of that model will affect performance shown on these models, right? Because if you would change the architecture of the convolutional neural network, maybe instead of Acer, TRPO will performance better. So that I don't think it's really quite clear which one to pick in that sense, because I'm pretty sure the architecture that you define first is an effective performance first. And another thing is that you said you run, let's say, Acer once, and then you run Acer to the old one, and then you saw that the second model did almost like 50% better. As far as I remember, it was 60 to 40 probability. So that means if you run each time against the most updated version, you will do better and better. At some point, it's going to converge. They will always have 50 to 50%, which means that's going to be your best option. Am I right?
I think so. I mean, that's what I would try. As to like selecting between the different agents or the different algorithms, I would probably want to understand what each one is doing better first, just to give an intuitive guide as to what I'm selecting between. Because these are basically treated as black boxes in this exercise, which, you know, is a nice place to start. It makes it more accessible rather than theoretical, but I think having a theoretical basis for what you're doing would be helpful.
Sure. Can you remind us again, what are these different 5 algorithms? Are they like a pricing model, or?
No, they're algorithms for training your deep network using reinforcement. And I can't really tell you much about them because I don't have a great understanding myself.
No problem.
It can be like just like an architecture, like when you do, for example, image processing, there are multiple networks, right? I guess they are just different architecture, deep neural networks.
They're different algorithms for training.
Yeah, it's almost it's more, if you want to, it's more like the equivalent of the optimizer you choose for training your model versus the actual architecture. So
I see.
So kind of like, you know, stochastic gradient descent or something along those lines.
Yes. So let's see if the paper will help highlight what I mean. Yeah, so basically what it like initializes your network, and then it iteratively takes some action based on some like strategy, heuristic network prediction. It gets information back from the environment, and then it accumulates gradients, and then it updates the gradients somehow. And then, you know, there's other stuff like if you're in a terminal state, clear stuff. That's what this particular algorithm is doing, but there might be different ways of accumulating your gradients, of you know, of factoring in information from the environment, so your new state, so the new game board, your new reward value. There might be different ways of like handling all of that, and so that's what the different algorithms are doing. Is there's a lot of different ways to incorporate the information and update your network. Sorry, I'm just looking for the actual algorithm itself, just to highlight how they might be different. I'm just skimming. I really haven't looked at these before. Usually there's an algorithm section. I don't see an algorithm section in this paper. Okay. Anyways, it's just a different app. Yeah, it's different like strategies for updating your network. So maybe one uses gradient descent, but another uses something else.
Awesome. Any questions, comments, feedbacks for Alexandra? This is a very interesting session.
I was just wondering if she's going to put her agent against the Dimitri's to see which one won. The heuristic one or the deep learning one. The whole idea is to try to do better with deep learning. We don't get to know the results. We're going to sit in suspense.
Well, did you get to submit it to the competition, Alexandra? Maybe we can get an idea of the score.
Yeah, she could do that.
No. Do you get to submit the whole file, or do you submit like a trained model? What is the actual submission?
I think it has to be a Python
Sorry, I can't hear
file.
you, Alexandra. Go ahead, Dimitri.
It has to be a Python file, they say.
Got it. So maybe it's a trained model that she loads the weights and takes the board state and returns a column as the next move. Cool, very interesting session. Be interesting also to play around with the OpenAI's Gym environment. That'd be interesting adventure we can explore in the future. Some funny comments in the chat. Cool. There's no more comments, feedback. Thank you, Alexandra. I want to thank you. That was a very interesting session, and thank you, Dimitri. Very interesting session as well. Let me go back to my screen. So that covered the 4 lessons, really interesting lessons for this module. There's another one that we're going to take a deeper dive. I haven't gotten the chance yet to spend a lot of time on it. That's why I keep postponing the meetup, so I apologize for that. But once I get some time, hopefully we can get together and go over this this last event, which is kind of interesting. You're training a model to explore space, basically, and find out new energy resources. I think build colonies and compete against other colonists in space. So it's kind of interesting approach. It uses also a slightly different game engine as well. Yep, thanks for going over the papers and the code. That's also something that we like to do every now and then. Alexandra, appreciate that. And then for our upcoming sessions, we have a happy hour next week. I know it's kind of emotionally, politically charged next week, so hopefully things will be smooth and peaceful and tranquil, and everybody will be safe. But so far we have just a session for Friday, just a happy hour, no slides, no recording, just to get to know each other better and forge a stronger community. Then the event that I moved a little bit later was this intelligent bots navigating in space. I just want to highlight this event that I just posted today. We'll be joined by some new great friends from the Kaggle team that developed courses for the Kaggle Learn module. Dan, Rachel, and Ryan will be joining us on Wednesday, on January 27th. Super excited to have them. We have a small agenda here with some questions about some advice and what is their experience in developing these courses, as well as some advice for us in our community. And it's always also good to know what kind of projects they're working on. And we have some information here about their background and what kind of projects they like to explore. So that's on Wednesday, and after that we have the space one, and that will conclude the adventure on Kaggle Mini Courses, which, as you've seen, we started. I don't even remember when we started, back in September 30th. So it's been a fun, interesting challenge and adventure, and I want to thank everyone. We're getting there. A couple more sessions. With that said, I will advertise this event. Please share it with your network. I really need your help to make sure that we have good attendance. The event will be recorded in case people cannot make it. And if you have any questions for our panelists, we have a small window in the end, but if you have any questions in advance, feel free to let us know on Slack so you have an idea. Cool. With that said, I'm going to stop the recording here. I'll leave the floor open for discussion. But if anybody wants to hop off, now is a good time. Again, I want to thank Dimitri and Alexandra for that great session.